everyone, welcome to the course on medical biomaterials. We will continue on these metallic biomaterials. Let us recap what we did on this. First we looked at what is Miller index of a plane. That means a plane has an unique identity which is represented by this Miller index. Then what is this lattice unit cell? That means each crystal is made up of certain repeating units, infinite repeating units, and that is called a unit cell. There are 7 classes of these unit cells, okay, and then there are 14 Brevis types. Okay. So, we looked at the 7 classes of unit cells based on the 3 sides A, B, C, and based on the 3 angles alpha, beta, gamma. Then we looked at the symmetry. There are different types of symmetry, that is the translational symmetry, the rotational symmetry, mirror symmetry, and so on. Why do we have to do all this? Because there is anisotropy of the crystals. That means the direction in which, for example, the load is acting, the number of atoms in that crystal will be part of it. So, that will affect the mechanical properties. So, for example, if it is a BCC and the direction of the force is across the longer diagonal, the BCC, the atom that is inside the body also will be part of it. So, the mechanical strength will be higher, the Young's modulus will be higher, whereas if the load is along one of the planes, that particular atom which is inside the BCC will not be taking place. So, the number of atoms come down. So, the Young's modulus also decreases. So, and so on actually. So, the mechanical properties are determined in the direction in which the force acts for a BCC or for a FCC or a HCP. Then we looked at something called a coordination number. That means total number of neighbors that each atom will have. So, what is the coordination number for BCC, what is the coordination number for FCC, what is the coordination number for HCP, and so on. And then defects, because when the crystal starts growing, it is not going to be completely perfect. There are going to be point defects, there could be line defects, there could be bulk defects, there could be impurities coming into it, and so on. So, we looked at defects because defects again is going to affect the physico-chemical properties of that particular crystal or the metal. Okay. Then we looked at grain boundary. As the crystal grows from different directions, they come and collide inside, and there are grains formed, and the grain boundaries determine the slip, their defects, their physico-chemical properties, and so on actually. Okay. So, grain boundaries are very important, and later on we are going to look at sometimes corrosion starts taking place along the grain boundary also. So, grain boundary plays a very important role in the properties of the metal. And then we looked at atoms of different sizes when they are part of the crystal. For example, sodium chloride, sodium and chlorine, how do they form a crystal? Or if I am going to add an impurity atom to the existing crystal. Okay. For example, in stainless steel we are having carbon, we are having nickel, okay, with iron. So, how are they going to fit into it? Are they of different radius, or are they of same radius? And so, what are the different sizes of atoms that could just fit into the gap left behind by other atom. Okay. So, all these we looked at in the past 3 or 4 lectures, and today also we will look at some more properties of metals. Okay. So, the crystal structure, like I said, chromium is a body centered cubic, cobalt is a hexagonal closed packing. Iron, interestingly, the packing crystal structure changes at different temperatures. At 900 and less than 912 it is BCC, it is FCC between 912 and 1394, it is again BCC around greater than 1394. So, if you look at molybdenum, for example, it is a BCC, nickel it is FCC, titanium at 2 different the temperature less than 900 it is HCP, above 900 it is BCC. Sodium chloride is FCC, aluminum oxide HCP. Polyethylene, this polymer, generally polymers will be amorphous, it will not be really crystalline majority, but again there are many polymers which are crystalline, or they could have a mixture of crystalline and amorphous. PE, polyethylene is orthorhombic. Okay. There is something called atomic packing factor. It is also called packing efficiency or packing fraction. That means fraction of the volume in a crystal that is occupied by the atoms. That means the opposite of the 1 minus that fraction will give you what is a void space. Okay, the void space, if it is minimum, then it will be a very strong crystal. If the void space is maximum, it is like a porous. So the strength is much lower. So the hexagonal closed packed, if you take HCP, the atomic packing fraction is 0.74. If you take face centered cubic, packing fraction is 0.74. If you take body centered cubic, it is 0.68. Simple cubic, and that means only the corner 8 are filled with atoms, it will be 0.52. Diamond cubic 0.34. So as you can see, it keeps going down, and HCP has the highest packing factor 0.74, then comes FCC, then comes BCC, and so on actually. How do you calculate? Okay, let us take a BCC for example. We have been seeing BCC. There is one big atom in the center, that is why it is called body centered, and then we have 8 atoms at 8 corners. Okay, so if you take the long diagonal, we have the big atom 2r of radius r, 2r is the length, and then another atom at the corner, both the corners. So this length is 4r. For a cube, the long diagonal is given by square root of 3 side. So if you take a as the side, square root of 3a should be equal to 4r. We looked at that long time back, right, for some other purpose also. Okay. Now how many atoms are there? Number of atoms is one big atom, that is part of this cube, and there are 8 corners, there are atoms, but these corner atoms are shared by 8 different cubes. So that will be 1/8 of multiplied by 8, that will be 1. Okay, so the number of atoms will be 1 plus 1, 2. Okay, number of atoms is 2. Volume of one spherical atom, okay, 4 by 3 pi r cube, 4 by 3, 3.14 into r cube. Now A I said is equal to 4r by square root of 3, right. So what is packing factor? Number of atoms, volume of one atom divided by the volume of this cube. Cube is a cube. Okay, so A is given here, so you can put it here, that will become cube. Okay, volume of one spherical atom is this multiplied by 2. So when you do all these, we get 3.141 into square root of 3 by 8, 0.68, right. So BCC is 0.68. That is how you get it. So it is a lot of geometry involved in this type of calculation. Packing factor is very important for you to know how well packed the crystal is, or what is the void space in the crystal. Okay. Fatigue is another important property which comes in of course even in non-metals. The maximum stress that a metal will withstand without failure for a specified number of cycles. For example, if you have heart valves, it keeps on moving, opening, moving, opening. So that is how many times we can do that. It is more important than tensile or yield strength, because heart valves, knee joints, all these undergo a lot of fatigue. Okay. So that is more important rather than the strength. Okay. Grain size reduction, like I said, grain boundaries are formed because as the crystal grows from different directions, they collide, and then there is a grain boundaries that are formed. So ideally, smaller the grain size, stronger will be the particular crystal. Finer and more homogeneous grain size leads to more homogeneous packing of the crystal, and it stops dislocation type movement. That means it will prevent a slip of each crystal. Okay. So it improves the toughness. So ideally in metals they like to try to reduce grain size. This can be controlled by slowing the rate of solidification. Okay. That means when it is cooling, do it very slowly, do not do it very fast, then you will have lots of big crystallites and there will be a lot of grains. Plastic deformation after solidification, that is, you have heard of in the stress strain graph, we have the elastic initial and then later on we have the plastic, right. So once it has cooled down, then try to deform it in the plastic. So all these will help in the grain size reduction. Okay. There is something called strain hardening. Okay. So ductile metals become stronger when they are deformed plastically, at temperatures well below the melting point. So that is called cold working. Okay, so you bring it down below the melting point and then they deform it plastically so that it gets very hard. Okay. The dislocation density increases with plastic deformation. So the average distance between dislocation decreases and the dislocation starts blocking the motion of each one. So they are not going to get dislocated further. Okay. Okay, then there is something called metal leaching, metal attrition, that is metal on metal joints. There are joints, there are metal and they start moving one on top of the other or one related to other. If there is going to be attrition, there could be metal leaching, okay, or sometimes debris leaching. This is a big problem in orthopedic biomaterials, knee joints, okay, especially there, because in orthopedic they use metals, titanium alloys, which mainly used for plates, screws, prosthetic, cobalt, chromium, molybdenum alloys for prosthetic, stainless steel for plates, screws, wire, polymers, polymethyl methacrylate as a cementing agent, ultra high molecular weight polyethylene as the prosthetic insert, ceramics, aluminum oxide for prosthetic surfacing, zirconium prosthetic surfacing. So you could have metal leaching or metal debris, even polymer debris are also possible, but more than polymer debris, metal leaching causes more problems actually, because elevated chromium, cobalt in blood and urine are observed in some cases. They can even form non-scale and large in number, unlike polymer. Other ions that are also released are titanium, aluminum, vanadium and nickel, but cobalt is the main chap, okay. That is a big problem. Chromium, cobalt toxicity can affect many organs, neurological problem, cardiological problem, hematological problem and endocrine problem. Chromium is less cytotoxic than cobalt, but it also induces interstitial cell damage, tubular necrosis, which can affect your renal, that means your kidneys. So especially knee joints, people who had artificial metal knees always find leaching of these metal in the blood. Let us look at a simple problem. This problem was taken from this reference. Calculate the number of cobalt ions released from this cobalt, chromium, molybdenum. Okay. This contains 65% cobalt, okay, of the head is 28 mm dia of a hip joint. The wear rate is 0.14 millimeter per year. Okay. Density of cobalt is 8.83. They want to find how many cobalt ions are released. Okay. So when it is released from the prosthesis, only 65% contains cobalt, okay, rest all is chromium and molybdenum. Okay. So let us look at the area, because we said the head 28 mm, okay, 4 pi 1.4 square. Okay. Now when you have hip joint, it is like a ball and socket, so only half of it is in contact with the socket. The ball, half of the ball only is contact, remaining half is outside. So we will take only one half. Okay. So we will divide this by one half. Okay. So this is the area, the volume is 1/2 of 24.63 into 0.014 centimeter per year, okay, because this is the wear rate. This is in millimeter, so I divided by 10. So many cc of cobalt, okay, so many cc of the alloy comes out, okay. Out of this only 65% is cobalt, so many cc of the alloy per year is coming out. Okay. So what do? We multiply by 0.65 because it is 65% cobalt. Okay. Density of cobalt is 8.83, and then you know this is the Avogadro number 6.023 10 power 23 divided by atomic weight is 58.93 here, okay, because we are converting that into mole. So that gives you 1 into 10 power 22 atoms of cobalt per year. Understand? So volume of the prosthetic is this much, 65% is cobalt, so we multiply by 0.65. Okay, now we are converting it into number of atoms. So how do we convert it? Okay, so how do we convert that? We divide by 58.93, multiply by Avogadro number, and also multiply by the density of cobalt. Okay. So 0.65 into 1 multiplied by 0.172 is the cc of cobalt. When we multiply by density of cobalt, that will give you gram of cobalt, that is 8.83. When we divide by 58.3, that molecular atomic weight of cobalt, that will give you a mole of cobalt. When we multiply by the Avogadro number, that will give you the atoms of cobalt. So 10 power 22 atoms of cobalt are leaching out when there is a wear of 0.14 of the hip joint. But of course, we are not going to have continuously cobalt purely dissolved. There could be debris also, small bits and pieces, but this will be the upper limit, but there could be debris coming out, it will not be like a single ions of cobalt, but it is a very interesting problem. So, so many atoms of cobalt comes out per year, and that based on the toxicity limits, it could cause certain cytotoxicity or systemic toxicity to the patient. Corrosion, that is a very big problem in metals. Corrosion, unlike polymers, metals face this because of oxidation. So the oxides of metals are formed, hydroxides of metal form, or sulfides of metal form. So there could be chemical reaction, there could be electrochemical reaction with the environment, reaction because of oxygen, because of enzymes that are present in the body, oxidoreductase. So they try to put in an oxygen into the metal. As you know, our body fluids are very corrosive. You have dissolved oxygen, we have enzymes, we have salts because it contains chloride salts. So all these are very corrosive, and that leads to corrosion, different types of corrosion we will look at. So rust, galvanic corrosion is a common and occurs when two metals with different electrochemical charges are joined via a conductive path. So if I have, for example, even your prosthetic which contains cobalt, molybdenum, chromium, so there could be galvanic type of, because of electrochemical nature. Or if you have a certain biomaterial with two different metals, one may act as an anode, other may act as the cathode, and there could be current, and hence there could be corrosion. So when we use dissimilar metals, in fact we should avoid dissimilar metals, and they were in contact, there could be current flow which will lead to this galvanic corrosion. So the anode may start going down, dissolving into the solution. Stress corrosion, cracking, extreme tensile strength, especially when I am using along the grain boundary, cracks could be forming, or if I am having screws very tightly fitting, there could be stress corrosion. Microbial corrosion, because microbes, we have sulfate reducing bacteria, we have oxidoreductase, all these can cause. Sulfate reducing bacteria activate in the absence of oxygen, generally anaerobic, they produce hydrogen sulfide and cause sulfide stress cracking. In the presence of oxygen, aerobic bacteria will oxidize iron to iron oxides and hydroxides. So some bacteria oxidize sulfur to produce sulfuric acid, which is again an acid which can lead to sulfide corrosion. So all these can happen. We can have anaerobic condition, hydrogen sulfide is formed, so sulfide stress cracking. In the aerobic condition, oxygen is there leading to oxides of iron, hydroxides. Sulfur sometimes is converted to sulfuric acid, which leading to again biogenic sulfide corrosion. So all these are possible because of microbes. For example, if you take a nitinol, it is a very popular material used in cardiovascular stents after an angioplasty. It is made up of nickel and titanium equal amounts. It can exhibit severe pitting and crevice corrosion, but surface treatment to form amorphous oxide prevents the corrosion resistance. So oxides can prevent corrosion resistance. Electrochemical polishing also increases corrosion resistance, and it reduces the nickel dissolution. So otherwise nickel may be dissolving slowly into that. If you look at titanium, aluminum, vanadium alloys, they are used in joints. They are very good corrosion resistance, but are subject to fretting and wear because the aluminum can start wearing out. Cobalt, chromium, molybdenum, sorry, this is a mistake here, molybdenum alloys are also resistant to corrosion, okay, in body fluids, but cobalt is a big problem. It gets completely dissolved and the surface oxide changes into chromium oxide. So, cobalt release is a problem. Okay. 316L, it is cheap, it is very ubiquitous, it is used quite a lot in orthopedic, but then it can go into corrosion, serious problem. Intergranular corrosion, because carbon is also present, and so the heterogeneous carbon present can lead to corrosion. Okay. Pitting arising from the breakdown of the oxide layer. Okay. So, there could be pits formed as the oxide layer gets fretting. Nickel and manganese are depleted in the oxide film, and the surface oxide composition changes mostly to chromium and iron with a small percentage of molybdenum in the human body. Okay. So, these start going out, that is called fretting. Crevice corrosion. So, when you have a bone plate and screws made up of 316L at the interface, the screw heads and the countersink holes, you can have this crevice corrosion. Galvanic corrosion, like I mentioned, if you have metals, dissimilar metals, combination of 316L and cobalt, chromium, molybdenum, or cobalt, chromium, titanium, aluminum, vanadium alloys, then you can have galvanic corrosion. So, 316 can have all sorts of corrosion. So, it is ideal material for only short duration and not for very long applications. Okay. So, you need to keep that in mind. Galvanic corrosion can also occur by using metal alloys that have undergone slightly different metal processing, cast versus wrought. For example, if you take cobalt, chromium, molybdenum, if you have two of these, one made through casting, another made through wrought method, then they can undergo galvanic corrosion. Okay. So, what are the methods? Barrier protection. We can have a surface layer, so that layer prevents the metal from contact with the atmosphere, air, water, greasing, painting, galvanizing, anodizing, oiling the surface, okay, coating a metal on another metal, electroplating. Okay. All these are barrier protection. Another is sacrificial protection, that means you have another metal coating on top like zinc or magnesium, which gets oxidized. So, it prevents the main metal from getting corroded, that is called sacrificial protection. Okay. You sacrifice some other metal which gets oxidized. Third is cathode protection. The metal object that is to be protected from rusting is connected to a piece of more electropositive metal like zinc. The anode is made up of more reactive element which loses electrons and get oxidized. So, the anode goes on disappearing and thus saves the cathode from rusting. Okay. So, zinc could be the anode, the metal which you want to protect could be the cathode. So, zinc will start going into solution and disappear, whereas the other material remains. Okay. That is called the cathode protection. So, different ways of barrier protections are possible. Okay. So, when there is a corrosion, iron becomes iron oxide. So, what could be the molecular weight change? Sorry, what could be the volume change? Calculate the volume change when iron of this density is oxidized to iron of this density. So, molecular weight of iron is this. Okay. So, it is quite simple. Volume of iron is 55.85 divided by 7 so this is 7.1 cc per mole. Molecular weight of iron oxide is 71.85, that means iron plus oxygen. Okay. 55.8 plus 16, that is 71. Volume of iron oxide is 71.85 divided by 5.95, 12.08 cc. Okay. So, we have the volume of iron, we have the volume of iron oxide. So, look at this, there is a big change in the volume. Therefore, the percentage volume change is 104.9 divided by original 70% change when iron gets iron oxide. So, when there is such a big change, what happens? These iron oxides becomes very unstable, very loose, it is like a flake, it is very porous. So, it loses all the mechanical properties unlike the iron. So, that is a big problem, you understand this problem. So, iron density is 7.7, whereas iron oxide density, reduction in density obviously, that means there will be an increase in the volume. Okay. That is about 70% increase in volume. So, how do you calculate? We use these density values. Okay. and then we use the molecular weight value. So, molecular weight of iron is 55.85, molecular weight of iron oxide is this plus another 16, 71.85. So, we take the molecular weight divided by the density to get Cc for both, then the volume change 4.9. So, it has changed from 7.1 to 12.0. So, percentage is this difference divided by original into 100, 70%, that is a big change. Okay. Now, let us look at electrical properties, because electrochemical corrosion is a very serious problem in biomaterials when we are using different types of metals joined together. So, we will look at it. Metals are good conductors of electricity. Okay. So, resistivity is the ratio of electric field to current density, and if you look at bone, resistivity is 46 ohms per meter, sorry, ohms meter, muscle is 2, gold is very, very low, ultra high molecular weight is very, very high when compared to these items actually. So, the polymers have very high resistivity, metals like gold have very low resistivity when compared to the various physiological body material. Okay. So, electrochemical corrosion, I said presence of dissolved oxygen, proteins, water, ions such as chlorides and hydroxide in the body fluid, and if two dissimilar metals are present, the one that is most negative in the galvanic series will become anode, the other one becomes cathode. What is this galvanic series? We will look at it. This corrosion is much more rapid than the normal. So, this happens biomaterials with dissimilar metals, mixed metals, or even inhomogeneity in the same material. So, if you have alloys, cobalt, chromium and so on, inhomogeneity, so one could be acting as anode, other could be acting as cathode, and there could be current flow and there could be galvanic corrosion. So, what is this most negative in the galvanic series? Let us look at the galvanic series electrochemical data. Lithium going to lithium plus minus 3.05 volts, sodium going to sodium plus minus 2.7, aluminum going to aluminum 3 plus minus 1.6, titanium going to titanium 3 plus minus 1.63, iron going to iron 3 plus minus 4 point, hydrogen going to 2H plus 0, silver going to silver plus 0.799, gold going to gold plus 1.68. So, most negative in the series will be the anode and the other one will be cathode. So, there will be corrosion that is taking place and that particular material will be dissolving. Okay. So, if I have here iron and a gold most negative, so this will become anode. Okay. So, Fe 2 electrons can become Fe 2 plus, so this can go into solution. Okay. That is why these gold, silver, even platinum can resist corrosion. That is why when you go into biosensors, lead wires, they always use the noble metals. Okay. So, look at this. So, most negative will be the anode. So, if I am having a aluminum and iron, this will become the anode and this will become the cathode. Okay. If I am having iron and gold, this will become the anode, this will become the cathode, and this is the reaction for iron, iron plus 2 electron, so you get Fe 2 plus. So, this starts going into solution. So, the electrochemical corrosion, galvanic corrosion is much more serious problem, and one needs to keep in mind when designing biomaterial, having dissimilar materials in contact with each other. So, you may have to have a ceramic, or you may have to a insulator or a polymer in between, so that the galvanic current is broken down. Okay. Of course, you can also have a micro corrosion, because the grain boundaries act as anode and the interior part acts as the cathode. Okay. So, there could be a current flowing and the grain boundaries could get disturbed. Sometimes cracks in metals can act as an anode and remaining metal can be a cathode. Okay. Because the cracks may have less amount of oxygen. So, there is a difference in homogeneity in the amount of oxygen present. So, that is called the micro corrosion. Okay. That also could be a serious problem. So, metals have this particular issue of normal corrosion because of presence of oxygen, because of presence of aerobic bacteria which oxidizes, sulfur reducing bacteria in the anaerobic condition forms hydrogen sulfide cracking, or even formation of sulfuric acid. So, then the dissimilar metal type of corrosion. So one is looking at using a passivating layer, looking at sacrificial materials and so on actually. Okay. Thank you very much for your time.